impact of yield, rework, and scrap on process capacity. A process or resource might not process successfully all the units, whether it is in a manufacturing setting or in a service. And we can define something called process or resource yield, right? This is the term as flow rate of units processed successfully divided by the total flow rate, or alternatively, 1 minus flow rate of defects divided by the flow rate, the total flow rate. So the way we can look at it, this is the resource, right? We have some input, some units, hopefully most or maybe even all units could be processed successfully, but if not all are processed successfully, we have some outflow here of defective units. So if no defects are made, yield would be 1, and this is what we considered in most processes so far. But if there are some defects, right, then yield is less than 1. So here is an example. Imagine we have a flow rate of 10 units per hour, but yield is 0.9 or 90%. Then, of course, the flow rate of units processed successfully will be 9 units, right? And so that's how the yield is defined, 9 over 10, right? This is the definition. And of course, flow rate of defects will be 1 unit per hour, right? So 1 minus 1 over 10 is again another way to calculate the yield, right? And of course, the question still remains, what do we do with those defective units? And the two options we have is either to fix those units and make them into right, functional good units, right? This is what we call rework, right? And the other alternative is to scrap or discard a partial or complete unit identified as defect, maybe because it doesn't make economical sense to try and fix something, or sometimes it's actually impossible. Regardless of whether we choose rework or scrap, the yield that is less than 1, right, less than 100%, will have usually an impact on process capacity. If we do rework, we might need additional resources, and rework then might consume additional costs. Or if we do rework on the same resource, then we reduce its capacity. And if we use scrap, then of course we will also have to start producing more units than we at the end need, and therefore the yield has again impact on process capacity. So in case of rework, all units eventually become good units, but some may take more time to process and may use additional resources. So rework can be performed on some additional resources dedicated to repairing the defects, as you see here in this picture at the top part, right? Let's say there is step 1, test, and then if this test fails, we go to the rework step, and then the step finishes all the production, then goes to step 2, and again test detects a defect, the rework is engaged. So maybe, rework could be performed by some experienced worker who can fix all the problems that are introduced by steps 1 to 3 by some less experienced workers. Or it could, or rework could be done on resources on which the units were produced and the defect happened. So, right, this is the bottom picture here. Step 1, then there is a test 1. If the unit is not working correctly, the unit goes back to step 1, and this loop may be performed maybe more than once, and then only if the test succeeds, the step 2 is engaged, and so on, right? Here is a numerical example. Suppose a resource can process 1 unit in 8 minutes, right? But 15% units are defective, and those units need additional 4 minutes on the same resource. And let me add here, which is not said here, that assume after those 4 minutes, the unit is guaranteed to be fixed. So what is the capacity of the resource? So of course, we can calculate the flow time, right, for a unit is 8 minutes, but with 15% chance there will be additional 4 minutes, right? So on average, the flow time will be 8.6 minutes, and therefore capacity will be 1 unit per, right? 1 unit is produced every flow time, or every 8.6 minutes, which gives us this capacity units per minute, or this in units per hour. It's almost 7 units per hour. Well, without defects, we can compare this to 1 over 8, which would be 7.5 units per hour. So you see the way that rework, or the less than 100% yield is causing a decrease of capacity from 7.5 to slightly below 7. And an interesting example of kind of extreme rework in services is intensive care unit after heart surgery, right? When you have a heart surgery, a patient with a heart surgery performed on him or her, then the patient goes to some intensive care unit, and in that unit, it might happen that the patient will get into a serious condition again, and the patient might be taken back for a surgery, and that would be an example of rework that may actually increase the time to process the patient significantly, and therefore reduce the capacity for operating, right? And even worse, it might be necessary to book additional capacity for those urgent cases where the rework, right, saving a patient's life might be necessary. An alternative to rework is scrap. Scrap is simply a situation where all defective units are discarded. They never become good units. Of course, we have a question on where to test, because if you have a process, as this example shows, with 3 steps, you can just run a final test that gives you a low cost of testing, right? And then you detect the defect, you scrap it or discard it. And if you have a good unit, you send it as a finished product. This has an advantage of having low cost of testing, perhaps one point at testing, one resource testing, but the disadvantage is that maybe the defect was introduced early in the process and we just wasted valuable time of step 2 or step 3, the resources that were performing those. An alternative is to test after every step, right? Test 1, test 2, test 3, after step 1, 2, 3, respectively, right? Of course, this helps save some capacity on step 2 and step 3 when the earlier tests detect defects. But the disadvantage is that we have much more testing to do. So the question is, again, which one is better, considering both pros and cons. Notice that when we have scrap to get n units, the expected number of units that we should start producing is n over yield, right? And so we will have to produce more. If yield is less than 1, we will have to start producing more than n in order to get n units of finished products or services. With m sequential resources also, right, notice that the yields are multiplying. So if I have, for example, 2 steps, each of them having 90% yield, the yield of the whole process will be 0.9 times 0.1, 0.9 times 0.9 equals 0.81, which is 81% yield. Consider this numerical example. Suppose yield is 0.8. Calculate the expected number of units that we should start producing in order to obtain 100 good units. Well, the answer to this question is, of course, use the formula that was shown here above, which is divide the number of units that you need by yield, which gives us 125 units. This is the number of units that we should expect as the starting, right, number. So we should start producing 125 units. Notice that if the defects are usually random, if they are random, that doesn't mean we will actually have to start producing 125. We will have to produce until we obtain 100 good units. Right, the number can be larger than 125 or smaller than 125, but on average, we should expect around 125 units that we need to process in order to get 100 good units. Some examples of scrap with very low yields are recruitment process. The first one is recruitment process. In a recruitment process, let's say if you know that out of, let's say, 20 applicants, you normally select just one good candidate for a job, then you know that if you want to hire 5 people, you might need to get at least 100 applications in order to have a good chance to have 5 good applicants, right? So in that case, the yield would be 5%. When another example is developing new medicine, again, the same principle applies. For a lot of tested, let's say, options, very few actually are useful or good, effective medicine. And so if the yield is, for example, 1%, you need to test much more, right? You need to test 100 different options to have a chance to find one good working medicine. So as I said earlier in this segment, the question still remains when to inspect, when is it best to inspect? And as we said, inspecting frequently is costly, right? Like in the second example here in this picture, but of course saves capacity of later steps. And the important observation is if, let's say, step 2 or step 3 is a bottleneck, it's important to test before the bottleneck because by that, we might be able to save the capacity of the bottleneck and not waste it on some units that are already known to be defective. When we consider scrapping units that are defective, there are interesting implications for the value of a good unit. So the question we want to ask at this point is, what is the value of a good unit in a process? And the answer is, of course, it depends. And let us consider 2 different cases. The first case will be when the process is demand constrained. So suppose demand is just 50 units a day and our capacity is 100 units a day, but that's capacity before we consider the defects, right? So maybe if we have some defects, we will actually lose some of that capacity, but let's say the defect rate, right, is still small, the yield is quite high, and maybe after the defects, our yield is 90%, so we still have 90 units capacity after adjusting for the defects, right? So we still have more than the demand, 50 units per day. And in that case, we will observe that value is always cost-based. Value of a unit that we have in the process that is still not detected as defective is cost-based. Why is that? Because if you detect a defect, all you need to do is throw it away and then make an extra unit. And if you make an extra unit, well, you just pay an extra cost. And why can you make an extra unit? Because remember, you have sufficient capacity. Your demand constraint, not capacity constraint, right? So basically, you do not lose revenue. All you lose by detecting a defect is you lose a cost of making an extra unit, right? And we can also actually calculate the value of a unit while it goes through a process, right? This cost will be basically increasing, right? So at the beginning of the process, before you start processing the unit, the value is just the cost of the inputs that you will use for the unit. But as you move through the process, you just add additional costs because maybe you add more inputs, maybe you process and you use valuable time of resources. So the value leaving resource I can be estimated as 1 over yield of resource I multiplied by value entering plus variable cost at resource I. A different calculation will be performed when the process is capacity constrained. When you have a capacity constrained process, the value will be, you will notice, cost-based. Value of a good unit will be cost-based before you reach the bottleneck, but after you cross the bottleneck, the value will be revenue-based. And why is this? Because again, if you detect the defect before the bottleneck, right, then you didn't waste the bottleneck's time yet, right? And therefore, all you need to do, assuming the yield is not too small, all you need to do is make extra units, right? Before the defect, you have extra capacity, unused capacity, because this is not the bottleneck. These are not the bottleneck steps. So you can just make extra units. And as this was the case in the demand constraint, right? You have extra capacity, so you just have to pay again the cost of making the additional unit to replace the defective one, right? And you still keep bottleneck fully utilized with hopefully good units. No revenue is lost yet here. That's before the bottleneck. But after the bottleneck, revenue will be lost. Why is that? Well, if you detect a defect after the bottleneck, then you have no way of replacing the unit with a new unit because the bottleneck is working at full capacity. And therefore, what you lost by detecting a defect now is you lost the opportunity to sell the unit. Of course, you might have, right, so you lost the revenue minus maybe some additional costs that you would have paid if this unit wasn't defective. However, basically, almost all the revenue is now lost, and even the small costs that might be the remaining costs of processing will decrease this opportunity, lost opportunity, but just a little bit, right? So this leads us to the observation that the cost arising from detecting a defect dramatically increases when the flow unit crosses the bottleneck, right? As we said, the value of the unit in this case, in the capacity constraint process, is cost-based before the bottleneck and revenue based after the bottleneck. So cost, for example, some units might cost you, $5 at certain point in the process, $10, $15, and then they might sell. The revenue might be $500, right? So there could be a dramatic increase in the value of a good unit as it crosses the bottleneck. And that actually tells you that, especially in capacity constrained processes, you should inspect prior to the bottleneck, because this is where you will get the biggest improvement in your profitability.